Before we move forward to characterizing the measure of randomness for a random variable, which we basically related to the problem of either generating unbiased coins out of a random variable or generating the random variable from unbiased coin. Both these formulations make sense. Before we address that question, we want to introduce an approximate version of that question. So the goal will no longer be to generate exactly unbiased coins or to generate a random variable with a given exact distribution p, but to generate a random variable with a distribution close to p. So that begs the question, how do you measure distances between distributions? What do I mean by saying that a distribution is close to p? So this is a bit of a digression. What I would like to do now is to tell you about how we measure distances between distributions. So we'll revisit this topic later, but it is an appropriate time to first to introduce this for the first time. So as you can notice probably in this course, rather than stating quantities upfront, what I've been trying to do is I've been trying to first motivate a question, first use a motivating question to set up a problem, and then introduce quantities as a natural answer to that problem. In that context, a very good candidate for measuring distances between distributions is this quantity which is called the total variation distance. Okay, total variation distance. This has many names. It is also called statistical distance. In some people call it statistical distance. I would say that statistical distance is a more popular name of this quantity in computer science and machine learning. Total variation distance is a more classic name. And it is very easy to define this quantity for discrete distributions, namely PMFs. So this is something which we'll encounter again and again in this course, just like entropy. This is one of the other main characters of this course. The first one was entropy. Second one we introduced today is this total variation distance, dpq. D for distance, p comma q. Okay, so it's the distance between p and q. This notation is defined as, so it's defined as half of summation over x in that alphabet calligraphic x, okay, of px minus qx, mod of that. Okay, so you go over all the realizations x and take px minus qx. That's what dpq is. It's well defined. You can check that this is a reasonable measure of distance, although it's not very important for our treatment, in the sense that it satisfies three properties. If dpq is 0, then px must be equal to qx for all x, therefore p is equal to q. So same points have distance 0. It's non-negative, that is also good. So it's 0 if and only if p equals to q, and it satisfies triangular inequality. That's something you can check. We'll come back to these properties later, but that's some quick sanity test. So dpq is less than equal to dp, let's say q prime plus dq prime q. You can check this. This one also holds. So this is a reasonable notion of a distance between distributions, and it satisfies certain properties. I'll just review few properties, which are essentially equivalent expression for this dpq. What you can show is actually this dpq is supremum over all. Supremum is like maximum. So its maximum, supremum is similar to maximum but requires some slightly more formal definition. It's maximum over all events A or over all subsets A of X of PA minus QA. So it is the maximum probability difference between two events. It's the maximum difference between probabilities of an event A under P and Q. That's what dpq is. From symmetry, this is also equal to maximum over B of QB minus PA, PB. And therefore you can also show that this is equal to sup over A PA minus Q. You can put a mod here because the maximum will be attained by a non-negative quantity. Okay, this is also true. Okay, you can show this. So I'm not showing these properties, but it can be shown. In fact, we can exactly write down which set attains this maximum, this supremum. So its supremum is a max when it can be attained, and this is indeed a max because it can be attained by this set, which I'm calling A star. It is the set of those x for which px exceeds qx. That's the one for which dpq is equal to the supremum. Okay. And similarly, this particular sup is attained by this set B, x such that qx is greater than px. So this is one property that will be useful for us. I would urge you to go back and study these properties carefully. This is something that you should recall quickly throughout this course. Okay. Another property of this DPQ is that it's always between 0 and 1. It is 0 if and only if P equals to Q, and it is 1. It can also be 1. You see, it's PA minus QA, so it's always less than equal to 1 because PA is less than equal to 1, but it can also equal 1. When will it equal 1? That's interesting. So equality on the right side holds if and only if the support of P and support of Q are disjoint. So what is support of a PMF or support of a distribution? Is the set of points on which a distribution P puts mass, and it's the support of Q similarly the set of point on which this distribution Q places mass. So dpq is 1 if and only if these two supports are disjoint. So if you think of this as your alphabet X, and suppose this is where P puts mass and this is where Q puts mass, so these are disjoint. There's no common point between them, and in this case dpq will be 1, and this is if and only if. Okay, so if this holds, then this is 1. If this is 1, then this must be true. You can also show this. We'll come back to that proof later. Finally, I would like to point out that this definition of dpq can be easily extended to continuous distributions, continuous random variables, more general distributions, distributions with density. So here is the example. Suppose your distribution has densities, suppose your two distributions P and Q have densities. So this is densities F and G. So density of P and density of Q. So suppose you have these densities F and G with respect to this standard Lebesgue measure, but I don't need to use that language actually. So when you think of a continuous random variable, you can think of its densities, and these random variables P and Q have densities F and G with respect to the length measure, and then you can define dpq simply as half of integral fx minus gx integral over x. Okay, just like we had summation earlier, now you have integral of density. So PMF gets replaced with densities, and you have integral instead of summation. This 2 is equivalent to supremum over a PA minus QA. Okay, and now equality holds if and only if it's a similar condition. So the set which attains equality, it's given by A star equals to the set of those x for which fx exceeds gx. Okay, that's the set which attains this with equality. So this dpq is this total variation distance is something that we would like to use as a measure of distance between distributions, and it satisfies various properties. For instance, it's always between 0 and 1. And so the important property that we saw in this part is this formula, that it is supremum over all APA minus QA. This is very important. Such formulae will be seen throughout this course, which take a quantity like this and relate it to max of some other function. Okay, so in particular they're useful because for any particular A, PA minus QA is less than dpq, and the best A, this bound holds with equality. That's one way to interpret such formulae. Sometimes such formulae are called variational formulae, and that's where this name. This distance is sometimes also called variational distance because you have this form for this distance. The name total variation distance is in fact associated with this form. It is something related to total variation, and that you can look it up, the reason for this name. But variational distance, total variation distance, statistical distance, these are all the same things, namely this distance, and we'll use it throughout this course. See you in the next lecture.